A single covalent bond is the sharing of two valence electrons. This only happens between nonmetals and hydrogen. This is different from an ionic bond because they actually form molecules where two specific atoms are joined, not like an ionic bond. In an ionic solid, you can't tell which atom the electrons moved from or to. Ionic compounds organize in a characteristic lattice. You can see an example of a lattice in this picture on the right here. You have alternating positions of negative ions and positive ions repeating over and over again. And again, you can't see where the electrons came from or to. And also, this is just a small representation of the whole. This lattice could be smaller, slightly smaller. It could be a lot bigger than what you see here in this picture. This isn't what a molecule is like. So here's how you show the formation of a molecule. It's kind of like a jigsaw puzzle. You put the pieces together and you end up with the right formula. When everyone's octets are happy, meaning they have 8 in their outer shell, or for its hydrogen 2, you know that's the correct formation. So here's an example, water. Water, of course, the formula is H2O. So let's just put the pieces together. Hydrogen has 1 valence electron, and oxygen has 6. So if I take one of the hydrogens, I can see that it will fit in the space right here. I have a unpaired electron where these two will kind of fit like puzzle pieces, like that. So the first hydrogen is happy. It wants 2 electrons. Remember, hydrogen only has the 1s orbital that can fit 2 electrons, and it has 2 electrons. So this hydrogen is good. Oxygen still needs 1 more electron. Good thing the formula for water is H2O, which means we need another hydrogen. So you can see if I have another hydrogen here with its 1 valence electron, it'll fit nicely in this space here. Now every atom has full energy levels. This hydrogen wants 2, it has 2. This hydrogen wants 2, it has 2. So they're both happy. Every other element on the periodic table, like oxygen, want 8, and this oxygen has 8. So everybody's octets are happy, and it means this is the correct formation. And the bonding here shows us that it is bonded on an angle like this, and it's because when we did the electrons in our Lewis dot structure, our electron dot structure, we did it correct according to the rules. So we know we have a place to bond a hydrogen on this side and then this side, and we end up with this bent structure. And this is very important for water, for it to be done this way. It can't be a straight line. I couldn't have put the hydrogen here because that would violate some of the rules of these electrons filling in that we learned in previous chapters. Sometimes we have multiple covalent bonds. This happens when atoms share more than one pair of valence electrons. Sometimes you have a double bond when the atoms share 2 pairs of electrons, or 4 total. You can also have a triple bond when atoms share 3 pairs of electrons. These 7 elements here, you should know them as diatomic. They're all molecules, and they're all commonly asked in the Chapter 8 questions. Some of these require single bonds, some of them require double bonds, some of them require triple bonds. But you should know that all of these are never alone as atoms. They always are bonded to an atom of the same kind, which makes them diatomic. So we have bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Each of these will always have a little 2 after them. So the way I remember all of these as diatomic is I say the letters all together in one kind of like a word, more of like a name. Kind of sounds like a German name, Brinkelhoff. So if you can remember Brinkelhoff, you can remember the diatomic elements. We'll be drawing a lot of them structurally in this chapter. Okay, but let me show you a double bond here for carbon dioxide. So whenever you have a structural diagram you're trying to draw and you have more than 2 elements, you have to decide which element is in the middle. This is very important. And the way you're always going to decide this is which atom is most metallic, which means the one that's furthest to the left. Now none of these are going to be metals, because remember this is a covalent bond. This only happens with nonmetals. But in our trend of metallic character, there's a sliding scale, and carbon is the most metallic because it's the furthest to the left. It's got the lowest electronegativity and lowest first ionization energy. So carbon's in the middle. So it has 4 valence electrons, so we need to fill them in correctly, 1 on each corner, like so. And it wants 4 more. Oxygen has 6 valence electrons. So here's an oxygen, 1, 2, 3, 4, 5, 6. And I'm going to need to attach 2 of these oxygens to one of these carbons. So let's see how this works. Of course, oxygen wants 2 more to be happy. So by attaching one oxygen, it's going to leave the oxygen 1 short and the carbon 3 short. So I haven't fulfilled anyone's octet here. Nobody has 8 in their outer shell yet. So let's see what happens when I attach the other oxygen. Now I have to put the other oxygen to the left of the carbon. I can't attach it here because remember, carbon is the most metallic, so that's the central atom. Everything has to kind of stem off of this carbon. So attaching the second oxygen is going to leave both the oxygen, leaves both of the oxygens 1 short and the carbon 2 short. So this molecule won't work with a single bond. So if you wrote O single bond C single bond O, you would be wrong because nobody is happy in that arrangement. So the only solution here is to share more electrons. So we take these unpaired electrons and throw them in the middle to make a double bond. We're sharing 4 electrons here. That is what is called a double bond. So now this oxygen is happy. It wants 8. It has 8. 1, 2, 3, 4, 5, 6, 7, 8. We're going to need to do the same thing to the other side because the other carbon's not and the other oxygen's not happy. So we're going to bring those electrons into the middle. Now we're done. This molecule actually required 2 double bonds to make everyone happy here. So again, we're going to count all the electrons each atom either has or shares. So this central carbon here has and shares 8 valence electrons. It's happy. So does this oxygen, and so does the oxygen on the right here. They all have 8 valence electrons. So remember, covalent bonds are when 2 nonmetals share electrons. Each covalent bond is a sharing of 2 electrons. Knowledge of valence electrons and the octet rule can be used to construct structural formulas of molecules. Now, sometimes this is really easy, like in the water example. Sometimes this is a little more complicated, like in the carbon dioxide example. In the next couple of videos, I'm going to show you a little trick, a little shortcut that will help you to determine how many bonds you need to draw. We still need to think about numbers of valence electrons and drawing our dot diagrams correctly, but with this little trick that I'll teach you in the next video, this will become a lot easier.